Hey, today we're going to look at the idea of work, what it means from a physics point of view, and how to do calculations involving work. So first of all, let's make sure we understand what we mean when we use the term work in physics. So we have two pictures here, a woman pushing a baby carriage and a man pushing on a brick wall. And the question is, which picture is doing work and why? So when we talk about the idea of work, we're really looking for two things. We're looking for, number one, we want to find some evidence that there is a force being exerted on something. And clearly, the first picture shows a woman exerting a force on a baby carriage. Second, we see this man exerting a force on the wall. So in terms of force, both pictures have that part of the work covered. The second thing we look for when it comes to work is we need some sort of a distance or a movement of the object in the direction of the force. So if we consider the woman pushing the baby carriage, there is certainly a distance through which the baby carriage moves while the woman is exerting the force. On the other hand, there is no distance when this man pushes on a brick wall. So in terms of displacement, we have it in the first picture, we don't have it in the second. That means that the woman pushing the baby carriage is an example of the physics definition of work. The man pushing on a brick wall is not. So let's take this idea a little further and make sure we understand it. Here it is, classic definition of it. Work is done when a force is applied and the object moves in the direction of that force. And when we have those two criteria, then we can start to look at the value or to quantify the work done. When we put a number to the amount of work done, we use the units of a joule. And a joule is broken into a Newton times a meter. So a joule is a Newton times a meter. So here we have the formula for finding work, and it says work, represented by the symbol W, is force, represented by the F, times distance. Now the distance in this case is given this combination of symbols, this triangle D, which really, the triangle is a Greek letter delta. And whenever we see that delta, it really means like a change in whatever happens after that. So in this case, work is force times change in distance, if you want to think of it that way, or change in position. So you can see that down here. The symbol for work is W, so W means work, and the units for work are going to be joules. Force, or F, is force, and that's measured in units of Ns or newtons. And finally, delta D is change in position in meters. So as we move forward, this is the relationship between work, force, and distance. The idea that work is equal to force times distance. Now, because the amount of work done on an object is found by multiplying the distance times the force used to move it that distance, both those factors affect the amount of work done. So you can get a lot of work done if you do a lot of force or a lot of distance or a combination of both. Now, what's really important, it's kind of a detail at first in science, and we don't run into this a lot, but it is possible that sometimes we have a force and a distance that don't perfectly line up. Imagine, for example, if we have a block of wood that's on the surface, like on the floor, and then we come along and push on this thing. We could push on this thing and exert a force that is exactly in the same direction as the distance it travels. They would be exactly horizontal. On the other hand, it is also possible that when we push on this thing, if we were a little taller, it is possible that we push on this object and because we're taller, we push kind of with this downward force on it. So maybe we're pushing with a force in this direction. Now you can see that the force is in one direction, and it's not totally different than the distance. The box is going to slide along the surface here. So the box is sliding horizontally, and our force is not exactly horizontal. So we have to make sure that the force and the distance are parallel to each other. So in this case, they're not perfectly parallel, so it wouldn't be right to use that force. But later on, we'll see that we can find that there is part of that force that is helping us move along. But for now, we want to make sure the force and distance are parallel to each other. They're in the same direction. And we're going to remember that all variables need to be in the correct units before plugging in the values for those variables. So before you put the values in, make sure you have your units correct. Nothing new there. All right, let's jump right into an example then. So here we have the example where a engine applies 1,000 newtons of force to a car and moves at 50 meters. How much work was done on the car? Well, in this case, it sounds like we have what we need. First of all, the force and the distance are in the same direction, so we can feel comfortable using the formula work is equal to force times distance. Then we are going to put the correct values in the correct places with the correct units, and newtons is what we want for force, meters is what we want for distance, so everything looks good there. So force of 1,000 newtons multiplied by 50 meters. And when we put them all together, we get 1,000 multiplied by 50. That would be 50,000. Now, the units, Newton times a meter is a joule, so we can just go ahead and write joules there. And now this is a skill that we want to work on as well. That's the correct answer from a physics point of view. That's how much work is done. But I want to remind you that we understand the idea of significant digits. And when you perform operations on significant digits, or with values that involve significant digits, you need to round your answer to the correct number of significant digits. So with this number, 50,000, it really can only have two digits. The two digits that we want to record would be the 5 here and the 0 here. Those are the only two digits we want to record. Now, do you see a problem if I just write 50 joules as my answer? That's a huge problem. I can't just get rid of these 3 zeros and still have the same amount. 50,000 joules is a lot less, or sorry, a lot more than 50 joules. So we need to make sure people understand that this number with its two significant digits is still a large number. And the way that we do that is we put this in scientific notation. So if the original number was 50,000 joules, imagine that the decimal for this number is sitting right around here, and we are going to move it 1, 2, 3, 4 places this way. In other words, we are going to write this number as 5.0, but that's too small. We got to remind people that it actually was a big number, so we're going to multiply it by 10. Now think of this, if we took 5.0 multiplied by 10, that would be 50. So 5, let me get my green pen here and just make sure this is clear. A little mini lesson in here about scientific notation. 5.0 times 10 would equal 50. That's still not enough. What if we put 5.0 times 10 times 10? In other words, times 10 twice. Well, that would be closer. That would be 500. What if we took 5.0? Well, if we wanted to get back to 50,000, we would have to multiply it by 10 once, twice, 3 times, 4 times, and then we would get our 50,000 joules. So we want a short way of saying take our 5.0 and multiply it by 10, 1, 2, 3, 4 times. So what we do is we use scientific notation and we go 5.0 times 10, but we don't want to write times 10 times 10 times 10 times 10. We just say times 10 to the power 4. So 5.0 times 10 4 times. That's the same as 50,000. But it has our answer to 2 significant digits. The rules for significant digits and multiplying is you cannot have an answer that has more significant digits than the number used that had the least digits. So the 50 has 2 digits in it. The 1000 has 4 digits. So we're going to go with only 2 digits in our answer. So final answer, work is 50,000 joules. Better yet, work is 5.0 times 10 to the 4th joules. Oh yeah, this part here does not count towards our significant digits. It's only this number or this part of this number here. All right, so 2 things here. How do we calculate work? Force times distance. And how do we correctly round our answers when we have a very large number like 5.0 times 10 to the 4? Okay, let's go on to another example. You push on a wall with all of your strength, 500 newtons, and it does not move. How much work was done on the wall? Good question. Typically, we would say work is equal to force times distance, or change in position. And then we'd get our numbers. Work is equal to 500 newtons multiplied by, now, what is our change in position? Oh, should have seen this. It does not move. So if it doesn't move, it's 0 meters. And 500 times 0 is 0 joules of work is done. So the work is no work is done if we do not move the wall at all. So from a physics point of view, no work done because we don't have the 2 things we need, force and a distance. If you're thinking about significant digits, 0 joules, I mean, any 0 answer, kind of, we can leave it as it is. It has as many or as few significant digits as you want. 0 is 0, so we'll just leave it as 0. Or we can make the statement, no work is done. All right, example number 3. You do 43 joules of work by applying a force of 5.21 newtons on a shopping cart. For what distance were you applying this force? Uh-oh, something's going on here. We've got a work, we've got a force, and in the formula, work is equal to force times distance. Now we know the information here for work, 43.0 joules. The force is 5.21 newtons. And we need to solve for the delta D, or the change in position. So going to take a little bit of math here. This is the value that we want. So the way that we approach this, I hope you've learned this before, is we do this kind of opposite operation. So if the delta D is here and it's in the numerator, so it's fine, just leaving it the way it is, we want to take this 5.21 newtons and move it over here. Okay? And the way that we do that is we are going to do the opposite operation. Because it's 5.21 multiplied by delta D, we are going to move the 5.21 to the other side by dividing by 5.21, and we're going to make sure we do it on both sides. So on this side, the 5.21 newtons times delta D divided by 5.21 newtons, well, 5.21 newtons here divided by 5.21 newtons here means that these 2 things are eliminated or cancel out. So we're left with delta D on this side. Well, that's great because that's what we want to know. So on the right side, all we're left with is delta D. On this side, we have the equation that we need to put into our calculator, or the numerical values we need to calculate. We need to get 43 joules and divide it by 5.21 newtons. So take out your calculator, take your 43 joules divided by 5.21 newtons. Oh, should have had mine handy. Here it is here. And on my calculator, I get 43 divided by 5.21. I get a whopping 8.25. So I get 8.2533 and a bunch of other stuff meters. So we're getting in this habit. When you're done and you have an answer that you like on your calculator, the 5.3221 on your calculator is great, but we need to write it in the correct number of significant digits. So our final statement will be this: the change in position, the distance traveled, is going to be, well, we did a division multiplication type question here. Dividing was the operation we did. And when we divide, we have to go back and look at which number had the fewest significant digits. This one has 3 significant digits. This one has 3 significant digits. So when we're done, our answer seems pretty clear, can have 3 significant digits, 8.25. So we stop here at the 5. There's a 3 following that, so it doesn't bump it up or anything, just like in math. It's less than 5, so we leave it the way it is. So our answer is 8.25 meters. So the final answer to the question, if you do 43 joules of work and you move 5.21 newtons, what was your average force? That's it. All right, last example. Car takes 45 meters to stop, and the brakes do negative 4,800 joules of work. This is new. What does that mean, 4,800 joules, but negative 4,800 joules of work? What is the force exerted by the brakes? Well, I guess if we think about a car driving along the road, in order to stop that car, here, let me draw a really bad version of a car. There's my car. It looks like carrot car. And imagine that this car is moving a real fast speed along the road. And I said, hey, we want to stop this car. Which way would you have to push on it or pull on it? Well, if you want to stop a car that's rolling to the right, you're going to have to get in front of that car. I wouldn't suggest this. Get in front of that car, and you're going to have to push it to the left to keep it from going to the right. So this idea of negative 4,800 joules, we'll see how that plays out with this question. But it's really saying that instead of pushing this thing forward as it moves forward and it gains energy, so we're doing positive work, this negative is telling us that there's some sort of loss or removal of energy. So we're going to do some work to take away some of the energy of this car, and that's exactly what brakes do. So how does that look mathematically? Well, if we're careful, it doesn't look a heck of a lot different than when we do positive work. We are strictly going to write in exactly what we're given in this question. So when the work was negative, it's negative 4,800 joules. Then the force will be here, and our change in different distance or position is 45.00 meters. So in order to rearrange and solve for force, we're going to leave the force right where it is there. I'm going to divide both sides by 45.00 meters. So I'll divide this side and this side by 45.00 meters. And on my calculator, 4,800 divided by 45, I get 106.6. So I'll write it right here. The force, when I take these two cancel out, when I take 4,800 divided by 45, my calculator spits out a big, long number, 106.66, etc. And that will be in newtons because it is a force. But we're going to round to the correct number of significant digits. Again, going back, there's 4 significant digits in this value. There's 4 significant digits in this value. So the grand total we can have in our answer is 4. So we can write this 106.6, no, not 106.6, 106.7. The 6 here is greater than 5. 5 or greater would bump this number. Same rules of rounding that you probably learned in math class. So we're going to write that as 106.7 newtons. And there really is no need to put this into scientific notation because we can express all the significant digits in a way that's readable. I would probably choose to leave it that way. But if you wanted to show off your abilities of writing 106.7 newtons in scientific notation, it would be 1.067, keep all the right number of significant digits, then multiply it by 10. How many times? Well, look how many times we moved the decimal. It started there and we moved it 2 places to put it here. So we need to take 1.067 times 10 twice. 1.067 multiplied by 10 squared is 100. So This is good. Leave it this way. It's easy. It's got all the significant digits. It's in a readable form. Nobody's going to complain about that. But if you're practicing significant digits, you would write this 1.067 times 10 to the power 2 newtons. All right, so quick introduction, but just down to the bare bones, what you need to know about work, force, and distance in the relationship. A little bit of math once you have that formula. But the math now involves units. Don't forget that. Like whenever we deal with physics outside of math class, it's not just math because we have units, and your answers always have significant digits. So always check those things when you're doing a question, but in particular when you're done. Do you have the correct number of significant digits at the end, and have you recorded a unit?